everyone, Changhun. We will talk on entanglement-enabled advantage for learning a bosonic random displacement channel. Sounds very interesting. And you can start.
Okay, yeah. First of all, thank you for inviting me here and giving me this opportunity to talk about my recent work. And as introduced, this talk is going to be about entanglement-enabled advantage for learning a bosonic random displacement channel. And you can find the details from this archive paper, this preprint paper. But I'm going to give you the big picture of our main result. And before I begin, I like to thank all the collaborators, like really many collaborators, especially Senri Chen. He equally contributed to this work, and also other like Yushikawa collaborators, Yat, Sisu, and Liang. And also I like to thank other collaborators from Caltech and Parameter, and also DTU. And I finished this work when I was in Chicago, but now I finally moved back to Korea, and I'm starting my new job in KAIST, so you can find me in Korea. Okay, so let me just give you some background here. So typically when many of the research in quantum information processing aims to find and characterize the quantum advantage using quantum resources. For example, quantum computation-wise, we hope to find some certain quantum algorithms that cannot be simulated using classical computers. And the main goal of the many recent experiments, such as random circuit sampling or boson sampling, aim to implement some experiment that cannot be efficiently simulated using classical computer. And also, we are hoping to scale up the quantum devices so that we can implement quantum, like larger scale quantum algorithms such as Hamiltonian simulation or Shor's algorithm. And another type of quantum information processing is quantum communication, using which we hope to transmit quantum information through quantum channel in a secure way. And another type of quantum information processing where we can find quantum advantage is quantum metrology or quantum measurement. So the main goal of quantum metrology is to achieve a sensitivity using quantum resources such as entanglement or squeezing, which cannot be done using classical means. And in this talk, I'm going to focus on a little bit different task, which is called learning from experiments. And I'm going to give you like what it means in the next slide. But by the way, you can interrupt me anytime if you have any question or comment. Okay, so then what I mean by learning from experiment. So let me just give you a really just high level picture. So how can a quantum computer or quantum devices help learning a physical system? Suppose we have a number of copies of some systems we want to learn here. So we have it can be a quantum system or a classical system. But what we can do if we have a classical computer or classical devices is to measure the system in a certain basis, and then we collect classical information. And then using this collected classical information, we change the measurement basis, and then we perform a similar experiment using the same copy, using an identical copy. And then we measure in a different basis, and we collect classical information, and we keep going. Then we're going to get enough, when we get enough classical information, then we can say that we have learned the physical system. But what's the difference if we have an access to quantum computer or quantum devices is that when you have a number of copies of a system you want to learn, then you don't have to measure each system, but you can store them at your quantum computer or quantum memories, and then you can measure in an entangled manner. So you can perform joint measurement across many quantum systems, so that, or like physical systems, so that you can extract more information than the classical counterpart. So it doesn't have to be in this framework, but this is kind of one framework people typically focus on. And using this framework, many people found that there is some quantum advantages. For example, like purity estimation of a given quantum system, or quantum state tomography, or like Pauli expectation value estimation, or Pauli channel estimation. So, and this is only a part of result in the literature, but one very relevant work to my work is this Pauli channel estimation. So let me just give you some idea of what's going on here. So the main task, the goal of this task for Pauli channel estimation is to learn all the Pauli eigenvalues of a given Pauli channel in epsilon error. So here, the number of qubits of this Pauli channel is n. And it has been shown that if we have a quantum memory access, then which is called quantum learning. In this case, you only need a number of copies that is only linear in the number of qubits, and that's already sufficient to learn all the Pauli eigenvalues within epsilon error. On the other hand, if you don't have access to ancillary modes and the entanglement, then you must use an exponentially many number of copies to achieve the same accuracy. So you can see that there is a rigorous exponential separation between the quantum learning and classical learning for this particular task. And our main question is in this talk is following. So many of these results are mainly focusing on these discrete variable systems or qubit systems. But in our work, we wanted to generalize those rigorous exponential separation in bosonic continuous variable systems. So we wanted to find some rigorous exponential separation for learning. But why it's very difficult is that in bosonic continuous variable systems, you will have an infinitely large, infinite dimensional Hilbert space. So that makes it quite hard to rigorously prove exponential separation. And our main technical contribution is to overcome this obstacle and improve a rigorous exponential separation. Okay, to do that, we focus on a particular family of bosonic channel, which is called random displacement channel. So let me define what it means. So we are going to consider n-mode random displacement channel, which can be fully characterized by a probability distribution P alpha, where alpha is an n complex number of variables. So alpha is alpha follows this probability distribution, and then following this probability distribution, we displace the input state with alpha. So here the displacement operator is nothing but a tensor product of single mode displacement operator across n modes. So here I like to emphasize that this n is the system size in this work. So as we're going to observe exponential separation as we increase the number of modes. So that's going to be the size of the system. And we can fully characterize the channel by the probability distribution, but we can also equivalently describe the channel using the characteristic function of this probability distribution, which means that it's a Fourier transformation, the Fourier transformation of the probability distribution. So I'm not going to go to the details of this, but by plugging in a well-known formula in bosonic systems, by just simply plugging in this expression in the channel description, you can find equivalent description. You can easily prove that they are equivalent. So like having a probability distribution is equivalent to having its Fourier transformation, because you can simply take a Fourier transformation, so that we can fully characterize the channel using this characteristic function lambda beta. And there are some examples. One of the examples is deterministic displacement unitary. So if you choose the probability distribution as a delta function, then the corresponding channel will be nothing but a unitary displacement operation on the input state. Or if we choose the probability distribution as a Gaussian distribution, then you're going to get a Gaussian random displacement channel, which often used to model the noise in bosonic systems. Okay, so then we're going to now define the task. So here the task of learning is learning the characteristic function lambda. So when because the channel can be fully characterized by this characteristic function lambda, so the channel is equivalent to learning the characteristic function. And we're going to focus, that's why we're going to focus on learning the characteristic function lambda function. And we want to show that there is a separation, exponential separation between two different types of schemes, two different family of schemes. The first family is entanglement-assisted scheme, and the second family is entanglement-free scheme. So for the entanglement-assisted scheme, you're allowed to prepare an entangled state between the system's Hilbert space and the ancillary Hilbert space, so that only a part of the state you prepared goes through the channel, and then now you can perform a joint measurement on the output state. Then you get a classical information, and then you can repeat this process to collect enough classical information about the channel you want to learn. On the other hand, for entanglement-free case, you're not allowed to prepare an entangled state between the Hilbert space in the system and the Hilbert space in the ancillary modes. So what you can do is only to prepare a particular type of quantum state, and then it goes through the channel, and then you perform a measurement to extract the classical information. And then you iterate the same procedure, but in between, you can also consider some adaptive scheme, which means that based on the previous measurement outcome, you can change your input proof state and also the measurement basis, so that you can optimize the information you can extract in the scheme. So we're going to consider these two different types of schemes to see if entanglement actually helps to enhance the sample complexity of learning the channel. Okay, and the main result is to prove an exponential separation between the learning with and without entanglement with ancillary modes in sample complexity. And more like roughly speaking, we're going to consider estimating lambda beta with arbitrary beta within error epsilon. And then what we will going to show is that if you want to finish this work, which means that estimating lambda beta within error epsilon, then if you use entanglement-assisted case, then the number of samples you need is independent of the system size n. On the other hand, for entanglement-free case, like for any entanglement-free schemes, we show that you must use exponentially many number of samples to achieve the same task. So this is the main result I'm going to present. And is there any questions so far? Okay, let me continue. So let me first give you some particular examples to make it easier to understand. So first example is about entanglement-free scheme, where you can't use any entanglement between your system and the ancillary modes. And the example is to use the vacuum state as an input, and then the vacuum state goes through the channel, and then you measure using so-called heterodyne detection, or sometimes it's called double homodyne detection. And so as I said, the input is vacuum and the measurement is double homodyne detections. And because you're going to get two real numbers for each output mode, we're going to get n complex numbers as an outcome when the number of modes in the system is n. And the explicit POVM of this measurement is written as a coherent state with a complex amplitude zeta vectors. And to see how to process the output of this scheme to learn this channel, we first examine the output probability distribution, and we describe this using the characteristic function of the channel. So by just directly computing the output probability distribution for this particular input and this particular POVM, then what we can show is that the output probability distribution is written as an integral of the characteristic function of the channel to be learned times this some phase factor times Gaussian envelope. So to make it clearer, so if we take an inverse Fourier transformation on this relation, then what we can show is that the channel's characteristic function can be written as the Fourier transformation of the output probability distribution times some prefactor. And by using this relation, what we can do is to construct an unbiased estimator for this characteristic function point. For example, after we perform this experiment n times, that means we're going to get a large n number of these complex vectors. Then how we process this is to take an average value over this e to the beta square times this phase vector motivated by this expression. Then we can show that this average, this estimator is actually an unbiased estimator of this lambda beta. That means that if we have a sufficiently large number of samples, and then we take this as an estimator, then our estimate will converge to the true value of the characteristic function, which means that we can learn this channel. Then the question is how many samples we need to guarantee that the estimate is accurate enough. And to do that, we use these Hoeffding inequalities, and then we can easily show that by looking at this expression, expression, we can show that the number of samples required to estimate this characteristic function within epsilon error is upper bounded by this exponential factor times some factors from these Hoeffding inequalities. So what's important in this expression is that there is an exponential factor depending on this beta square. And I like to emphasize that you don't have to know which beta you're going to compute. So you can see that in this experiment, you don't have any dependence on beta. You just implement this experiment many times, and then you get many classical information. And then if you want to learn a certain point at this function value at certain point beta, then you just process this using this output, these outcomes. And then if you want to estimate for different beta, you can still use the same expression, but by simply changing this beta using the same measurement outcomes. And for as you can see, if you want to learn this lambda beta at large beta, then you're going to have an exponentially large number of samples to learn. And what it means is that this sample complexity depends on the amplitude of this beta. So let me also go to the different scheme here, entanglement-assisted scheme, a particular entanglement-assisted scheme, where we are now we are allowed to use entanglement, so that we are going to use so-called two Moore-Squeeze vacuum state as an input state. So only a part of the system goes through the channel, and the other part of the state goes through, say, quantum memory, so identical channel, so identity channel. And then after that, we process the output state by performing some joint measurement or entangled measurement, which is sometimes called a continuous variable Bell measurement. Then after that, we get, again, these n complex numbers as an outcome. And then we compute, by computing the alpha probability of such a setup, then we can see that the alpha probability depends on the channel's characteristic function in the following way. And you can see that very similar expression appears, but the difference is this prefactor. I'm going to compare this to the previous schemes and this scheme like in the next slide. So let me just follow the same procedure. So we take the inverse Fourier transformation to get the expression that of between the characteristic function and the alpha probability distribution. And we again construct the unbiased estimator when we collected large n number of samples. And then by applying the same procedure, which is Hoeffding inequalities, then we can show that the sample complexity depends on the prefactor of this, that depends on beta, and also some accuracy and the failure probability. Okay, now I'm going to compare these two particular schemes. Now, what we obtained is following. So if you want to achieve an estimation error epsilon with high probability 1 minus delta, then the number of samples required for each scheme was given by following expressions. To make this the difference clearer, I'm going to consider a particular regime where the beta square is upper bounded by kappa times n, where n is the number of modes, so the system size, and the kappa is a constant. And then I'm going to choose the squeezing parameter of the two Moore-Squeeze state as a increase that increases logarithmically in the system size. Then we can show that the number of samples required for entanglement-assisted scheme is independent of the system size n. So you can always efficiently estimate lambda beta when beta square is upper bounded by kappa times n. On the other hand, for this entanglement-free scheme, a particular entanglement-free scheme, you need an exponentially large number of samples to perform the same, to achieve a similar performance. So you can see that there is an exponential separation between these two particular schemes. So we can see one example of exponential separation. But of course, this is not there, but I have to make some remarks here. So because we are comparing with a very specific entanglement-free scheme, so there might be a possibility that there is a better entanglement-free scheme exists. So we have to prove that this exponential separation holds even for most general entanglement-free schemes. So that's what we are going to do in the next few slides. And also another thing is that assume that the screening parameter can be chosen like very large. So this is logarithmic, but still, if we choose the number of modes to be sufficiently large, then the screening parameter R has to be really large. But in practice, this R is highly limited by some constant in experiment. So when I compare between this entanglement-assisted scheme with the entanglement-free scheme, I'm going to consider a fixed screening parameter later. But still, like theoretically speaking, we can already see a signal of this exponential separation. So let me visualize these two schemes a little bit more. So suppose we had a random displacement channel with a particular probability distribution, which has some oscillation or oscillatory behavior with a Gaussian envelope. And if we take a Fourier transformation to see the characteristic function, then we can see that there is 5 different peaks. So at the center and also for different directions. And if we perform the entanglement-assisted scheme to learn this channel, then what we can show is that the output probability of this entanglement-assisted scheme is almost identical to the probability distribution of the channel. And also, if we take the inverse Fourier transformation of the output probability to get the characteristic function of the output probability distribution, then this is also almost identical to the channel's characteristic function. So that means that we don't lose any information for this scheme. On the other hand, if we used the entanglement-free scheme, this particular entanglement-free scheme, then you can see that the output probability distribution is highly blurred from this the true probability distribution, so that you cannot see a clear oscillatory behavior in your output probability distribution. And also, it's clear from this characteristic function picture that these 4 peaks that is kind of a signal disappeared for this scheme. So that means that learning this particular random displacement channel becomes very difficult if we use this classical or this entanglement-free scheme. Again, this is a very particular scheme, so we need to consider more general entanglement-free schemes to rigorously prove an exponential separation. Okay, so before I go to so I'm going to talk about this entanglement-free scheme, most general entanglement-free scheme in this work. So again, let me recall that the entanglement-free scheme we consider looks like this. So we first prepare a state in the system, and it goes through the channel, and we measure, and we get a classical information. And using this classical information, we prepare another state and measurement setup. And then the state goes through the channel, and then we measure and we collect another classical information. And we keep going, and then we're going to get enough classical information. So this is the entanglement-free scheme we are going to consider. And the task, this learning task, I'm going to more rigorously define the task here. So for a given random displacement channel, the learner, I'm going to say Bob, the Bob performs learning scheme, like entanglement-free scheme, after which only classical information is stored. So as I said, after each measurement, after finishing this learning scheme, the Bob will have only a classical information. then the learner is asked to estimate lambda beta at some beta. So beta is not revealed at before learning this task. So after finishing all the measurement, then Bob is asked to estimate lambda beta at some beta using his stored classical information. So the reason why I emphasize that the Bob is asked to estimate lambda beta at beta later is that if Bob already knows that which lambda beta he's interested in, then Bob might construct a very specific scheme to learn lambda beta point. But because we hope that Bob learns this characteristic function for arbitrary beta, so that this the point beta will be revealed later after he finishes this learning phase. And as we already showed that this entanglement-assisted case, this using two Moskowitz vacuum state and Bell measurement solves this task with a sample complexity that is independent of the number, the system size, which is the number of mode. And then our main theorem is informally stated in the following way. So any entanglement-free scheme requires an exponential sample complexity to succeed with this task with high probability. More precisely, the number of samples has to be lower bounded by some exponential factor with constant kappa. So that this main theorem essentially says that there is an exponential separation between an entanglement-assisted scheme and entanglement-free scheme. So let me just give you some high-level this proof idea. So to prove this exponential separation, so to prove that any entanglement-free scheme takes exponential number of samples, we construct a hypothesis testing, which can easily be succeeded with high probability if Bob can learn this characteristic function well. So that means that if Bob has n copies of channel, and then if he uses this number of n copies of channel to learn this lambda beta, then he can succeed it with this hypothesis testing with high probability. That means that the statistical distance between these two hypotheses constructed in the first bullet point has to be large, because statistical distance has to be large to make it easy to distinguish them. And more specifically, the derivation distance between these two hypotheses has to be large enough, which means that in this case, it has to be some constant, like say like 0.2. And here, to be clear, the derivation distance is given by the difference of this probability distribution with the absolute value. Okay, and then so first of all, we show that we're going to show that for a constructed hypothesis testing, the derivation distance has to be large enough. And then we independently show that each copy of channel Bob has very small amount of information, which means that the contribution to derivation distance is exponentially small. That means that to achieve a constant amount of derivation distance, you will need exponentially large number of samples to because each copy only gives you an exponentially small amount of information. So that that concludes that the number of copies n must be exponential in the number of modes. So let me just give you a more specific proof technique here. So we are going to consider this 3-peak random displacement channel here. So the family of channel we are going to consider looks like this. The characteristic function always looks like this sum of these three factors here. So three Gaussian shaped functions. The first function has a peak at the center, and the second function has a peak at gamma, and the third one has a peak at minus gamma. And then gamma is its Fourier transformation in probability space looks like oscillatory. Again, this has an oscillatory behavior as previous example with a Gaussian envelope. And we're going to define two hypotheses with equal probability using this 3-peak random displacement channel. So for the first hypothesis, we always choose gamma equal to 0. So that means that the second and the third functions cancel out so that we have a peak at the center. So this is a single peak channel. But for the second hypothesis case, gamma is sampled from a random Gaussian distribution, so that the channel now has three peaks when gamma is sufficiently far from zero. So now the second channel will have these three clear peaks. So this is the hypothesis testing I'm going to consider introducing the previous slide. And then the task is to, for a given n copies of channels, decide the correct hypothesis. So for a given n copies of channel, Bob is going to use his learning scheme, like entanglement-free scheme, to learn this channel. And then Bob wants to tear apart between these two hypotheses. And note that because these two channels has a very clear difference at gamma, at this characteristic function space at gamma, that means that if Bob can learn the function value at gamma, then Bob can easily distinguish these two hypotheses very well. So that means that the statistical distance between these two hypotheses have to be really large. So to make it more concrete, let me give you first the learning phase. So Alice randomly samples gamma that follows a random Gaussian distribution as introduced in the previous slide. And then with 50%, Alice just ignores this gamma and just prepare the channel, the single peak channel, which means that gamma equal to 0 channel, and gives it to Bob with n copies. Or Alice really follows this gamma and then choose this 3-peak channel with n copies, and then she gives them to Bob. Then Bob now has to distinguish these two hypotheses using his learning scheme. So Bob is going to run his learning scheme on n copies of this channel, and then he obtains classical information. So basically, he collapses all the quantum information into classical information after this finishing this learning phase. And then now Alice is going to reveal this which gamma she chose. So like she sampled. So as I said, Alice already sampled one gamma, and then if she followed this gamma, so she picked a second hypothesis, then Bob will see these 3 peaks clearly if he learned well. On the other hand, if Alice chose the first hypothesis, then this gamma may not follow the channel she chose. But in any case, if Bob estimate lambda gamma, then he can easily distinguish these two hypotheses. Maybe let me give you a more clear picture here. So Bob prepares his entanglement-free scheme, and then he has learned the channel. And then if the gamma Alice reveals satisfies this condition, so gamma is sufficiently large, but at the same time it's not too large, then Bob can query this lambda gamma to see whether this is closer to 0 or some epsilon. So this is a good strategy for Bob, because if Alice chose the first hypothesis where there's no peak at gamma, then Bob will see that there is this lambda gamma is approximately 0. On the other hand, if Alice chose this 3-peak channel, then Bob will see a clear peak at lambda gamma. So if Bob succeeded with learning the channel well, then Bob can discriminate the two hypotheses with high probability. So that means that, and also if the gamma is too small or too large, Bob simply randomly guesses the two hypotheses. So he doesn't use this learning, his classical information, but that's already enough to succeed with the hypothesis testing, because gamma satisfies this condition, the first condition with high probability, which can be shown using the Gaussian distributions property, so that the Bob's success probability for the hypothesis testing has to be large if he can learn this channel well. Which means that more precisely, mathematically, that we can show that the total derivation distance has to be large between these two different hypotheses. More precisely, we can show that the average derivation distance with a random variable gamma has to be larger than certain like constant number. And as I promised, we independently show that the average derivation distance has to be exponentially, has to be upper bounded by some number. And I'm gonna skip this proof. This is quite important part, but this is too technical, so I'm gonna skip the proof of this this inequality. But if we combine the first inequality that I showed in the previous slide and the inequality here, then we can have these two another inequality between the left and right. Here, the right-hand side has two factors. The first factor is that the number of copies Bob uses, and another factor is some exponentially small number. So that means that if we like simplify these inequalities, then we can show that the number of copies has to be larger than some number that is exponentially large in the number of modes. So that we can show that we can prove the theorem, which is essentially to show that the number of copies you need has to be lower bounded by some exponentially large number in the number of modes. And so that means that we concluded our main theorem, which shows that any entanglement-free scheme requires an exponential number of samples to succeeded with this learning task with high probability. And as I said, as I showed in the first few slides, the entanglement assist case only requires a number of samples that is independent of the number of modes. So that concludes exponential separation between the entanglement-free scheme and entanglement-assisted scheme. And finally, we also consider some effect of loss to make to show that this is really practically achievable. This quantum advantage is practically achievable. And the main noise source in optical system is the photon loss. So if we consider loss for the preparation step and the loss in the measurement step, and we can show that using the similar technique. So the relation between the characteristic function of the channel and the alpha probability distribution, we can show that the loss effect is nothing but to reduce the squeezing parameter effectively. So if the loss rate is not too large as in practice, then the exponential separation still holds. To see how large advantage we can expect in experiment, we first consider the quantum advantage in lossless cases. So here we're comparing different schemes. So here entanglement-assisted scheme, which means that we are using entanglement with different squeezing parameters. And also we compare this particular entanglement-free scheme where we use vacuum plus heterodyne detections. And another scheme is the lower bound of the entanglement-free, which we proved using the theorem. And you can see that when the system size is not too large, then maybe we don't see any advantage here. But as we increase the system size, now you can see a clear advantage over the entanglement-free scheme, this particular entanglement-free scheme, or even for most general entanglement-free scheme. For example, when kappa is equal to 1 and the number of mode is 20, then you would need about like 10 to the 4 number of samples to achieve a certain accuracy. But if you're not allowed to use entanglement, then you are going to need a kind of 10 to the 7 or 10 to the 8 number of samples to achieve the same task. So you can see that there is a large amount of advantage even in practice. And also even in lossy cases, so which is more important in practice. So even in these practical cases, we can show that with a moderate amount of squeezing parameter and the moderate amount of loss rate, we can achieve much better sample complexity than the entanglement-free cases. So that means that our scheme can be implemented and also demonstrated in practice in the near future. Okay, so this is it. Let me just conclude. So we have shown an exponential separation in sample complexity of learning a bosonic channel, more specifically random displacement channel with and without ancillary. And as we showed with some realistic parameters like loss and squeezing parameter, this practical exponential advantage can be achieved, are expected. And some other tasks we hope to do in the near future is to prove a little bit more entanglement-free schemes, more general schemes, where your Hilbert space is still restricted in the system size, but you are now allowed to have some amount of quantum memory, and you can use this quantum memory for the next step, but you are not allowed to have an entanglement between memory and your system. So in the DV case, we have shown a similar exponential separation, but in this bosonic case, we haven't finished this. And another important outlook is this application to finding applications. The main motivation of generalizing this DV system to CV system was to find more practical applications, but this very particular, this random displacement channel, we couldn't find a good example of applications. So we are hoping to find some application in the near future. Yeah, thank you for your attention.
Thank you so much.